Hello students, welcome to this lecture. In the last lecture, we had been discussing the excited states of helium atom and how we can address this problem using degenerate perturbation theory. We will continue our discussion from there in this lecture. Just to refresh your memory, helium atom's excited states, we formulated 8 by 8 problem because we saw that the unperturbed system had 8-fold degeneracy. So, that means we could design 8 number of different functions which corresponded to same energy value. But then when we looked at the secular equation of the order 8, we realized that this the secular determinant that had many matrix elements as 0. So, they got converted to 4 different blocks, each block having a 2 by 2 matrix. Now, what we are doing in this afterwards, we considered one block. So, this block corresponds to psi 1 and psi 2 of the wave function. So, we would come to that in a moment's time. So, similarly, there are 3 other blocks that we would look how they are going to be. So, the problem at hand became a somewhat simpler problem, a 2 by 2 problem, where the matrix elements H prime 1 1 or H prime 1 2 we evaluated as Coulomb integral, that is J 1 S 2 S, or the exchange integral, that is K 1 S 2 S, where this is a Coulomb or exchange interaction between electron of 1 s orbital and electron of 2 s orbital. When we solved this equation, we obtained 2 different energy values. They were the first order energy correction to E1 and E2, which are 2 degenerate states in the unperturbed system. So, we see that the first order energy correction shows that the 2 energy levels will have different first order correction. So, therefore, the degeneracy of these 2 levels is going to be lifted, and the energies depend on the Coulomb and exchange integrals. When we looked at the wave functions that we obtained by using the coefficients from this equation C1 and C2, we see that phi 1 0 turned out to be the negative combination psi 1 minus psi 2, and phi 2, the second excited wave function, became the positive combination of the 2 functions, where psi 1 is given as when electron 1 is in 1s orbital, electron 2 is in 2s orbital, and psi 2 is simply the exchange of it. That means electron 1 has gone to 2s, electron 2 has gone to 1s. So, this 2 exchange term, one is psi 1, another is psi 2. Psi 1 minus psi 2 gives me phi 1, the lower of the 2 eigenfunctions, the lower of the 2 eigenfunctions, and psi 1 plus psi 2 is the higher excited state. We also discussed that when we look at this function, when the distance between the 2 electrons, that is, if I plot R1 minus R2 in the x-axis, when the distance of between these 2 electrons becomes 0, you would see that this function will simply become 0, because the first term and second term will become equal to each other, and then they will cancel out and we have 0. When I plot phi 1 square, that is the probability corresponding to this function, I would see that the probability of this phi 1 0 becomes 0 when R1 minus R2 is 0. That means, when 2 electrons are spatially located at the same space, the wave function vanishes. In other words, the one electron avoids the other, both the electrons are avoiding each other. So, therefore, they are never to be found together at the same place. And that situation goes by the name of Fermi hole. The second situation, when I look at the second wave function, the excited state wave function, I see that when R1 is equal to R2, this wave function does not become 0 first of all, rather its value increases. So, therefore, if I plot phi 2 square, I would see a slight increase in the probability when R1 is equal to R2. So, in other words, corresponding to this wave function, I would see if electron number 1 is present at a particular location, electron number 2 would have higher probability of being found at the same location. So, this situation goes by the name Fermi heap. That means, there is a heap here, there is a hole over there. So, we have this Fermi hole and Fermi heap, which have pure quantum mechanical origin. they do not represent the situation that the electrons are negatively charged particle or they avoid each other or anything like this. We cannot explain them in classical sense, but this Fermi heap, for example, finding both the electrons spatially at the same position is somewhat puzzling. But we will address these two problems, the two situations, Fermi hole and Fermi heap, in a moment's time. But before that, we would explore one other condition of the one other situation with respect to these wave functions. When I look at this wave function phi 10 and phi 20, I know that when I have a many electronic system, my wave function, in addition to being the well-behaved wave function from Born interpretation perspective, in addition to that condition, I also must satisfy another condition. That means the wave function must be antisymmetric with respect to interchange of any two particles. And this condition is comes into force when I have system where there are more than one particle. So we discussed this condition this in terms of spin statistics theorem in an earlier class. Now when I look at whether these two of these two functions, which one is symmetric or which one is antisymmetric with respect to electron exchange, you would immediately find the lower wave function phi 10 is antisymmetric with respect to exchange, because if I act permutation operator P12 on it, you would see that this phi 1 will become negative of itself. So therefore, this is antisymmetric with respect to each other. So that means if I apply electron exchange with respect to 1, 2, this function will become 1s2, 2s1, and this function will become 2s2, 1s1, which would be negative of phi 10. So therefore, this is antisymmetric. On the other hand, the second function is actually symmetric with respect to exchange. While antisymmetric satisfies the condition, this one phi 2 would be creating trouble. But then we know that when you talk about this, the requirement of the wave function to be antisymmetric with respect to exchange of two electrons, we mean that the wave function in its full form, that is spatial as well as the spin component. So now we have to incorporate the spin part of the story. So I have got two electron problems. So therefore, each electron brings spin with itself, because spin is an integral part of the electron. So therefore, I can construct the two electron spin functions. So we have discussed this in an earlier case. When I have two electron spin functions, I can have the total spin of the system becomes S1 plus S2, where S1 is the spin of one electron, that is half, the S2 is spin of the other electron, that is again half. So I can have two spin states, S equals half plus half, that is 1, or S equals half minus half, that is 0. So corresponding to S equals 1, I will have three MS values, MS minus 1, MS plus 1 and MS 0. They form a triplet state, and corresponding to S equals 0, I will have a single state, that is MS equals 0. So therefore, I have one singlet state and I have one triplet pair of states. So these four functions represent the complete set of spin functions for two electronic systems. Now the first three terms, three functions are the part of the triplet solution. The last one is a singlet one. We can establish that by evaluating the expectation value of S operator for each of these functions. Now what you see is that the triplet set is symmetric with respect to electron exchange, while the singlet one is antisymmetric with respect to electron exchange. Now we require that the overall wave function must be antisymmetric with respect to electron exchange. So what we will do is that we will couple this antisymmetric function, spatial antisymmetric function, with the spin part, spin symmetric, and we will take this orbitally symmetric part of the function with the antisymmetric spin function. So when we couple the symmetric with antisymmetric and here antisymmetric with the symmetric spin function, we would get both the ground as well as the excited state wave function to be antisymmetric, overall antisymmetric when I consider orbital nature and spin nature of the electron together. So this is what we will do. We will write down this wave function with the spatial part and this triplet spin part. When I do this, you can have first term with alpha 1 alpha 2. So, when you multiply this alpha 1 alpha 2, you would see that 1s orbital which contains electron 1 is now having spin of alpha, 2s orbital which contains electron 2 also has spin of alpha, and similarly when you consider beta 1 beta 2 or alpha 1 beta 2 plus beta 1 alpha 2. Now, you can open this equation these terms and rewrite them. I would strongly suggest that you please do this exercise independently. So, you open this function and then rewrite this function, then you would see that the first one of these, so I am coupling now the orbitally antisymmetric with this triplet symmetric functions. So, therefore, I have got 3 different functions. So, these 3 different functions represent the 3 different wave functions for this triplet state. The first one contains both the electrons in 1s orbital and 2s orbital with alpha spin. So, both electrons having alpha spin. The second one represents the situation when I have both the electrons in beta spin. So, this bar over this orbital represents that this electron is in beta spin. So, we are talking about an orbital's particular spin orientation, whether it is an alpha part or beta part. So, the bar indicates beta, without bar it indicates alpha. So, we will come back with little more details on this. And the third form I get as a linear combination of 2 terms, because I have got alpha 1 beta 2 plus beta 1 alpha 2. So, when I open this term, I would be able to write down this. These determinants are called Slater determinants. What are their features and all, we will discuss that in a moment's time. But the point is, when I couple this antisymmetric orbital function with symmetric spin function, I generate this overall antisymmetric. Similarly, I can take this orbitally symmetric function and couple them with the spin antisymmetric function and generate phi 2 0, which is overall antisymmetric. This would be that function. So, now if you can go back and recall where phi 1 0 had this Fermi hole, whereas phi 2 0 had this Fermi heap. So, in case of Fermi heap, what we had found is that 2 electrons were simultaneously present, 2 electrons were present at the same spatial location. So, that problem is now resolved, because we see that when the orbital function is phi 2, that is psi 1 plus psi 2, in that case the spin function is singlet. That means both the electrons have now opposite spins. So, therefore, that does not violate the Pauli's exclusion principle, rather it facilitates that. What we see here is that there are 2 electrons which can occupy the same spatial position, but can have different spin. So, therefore, they do not have all the 4 quantum numbers identical. So, that Fermi heap does not violate that principle. So, in other words, we saw this Fermi hole and Fermi heap, which arise because of the way we have taken our wave function. We have incorporated the electron exchange and we are requiring the wave function to be antisymmetric with respect to electron exchange. So, this Fermi hole and Fermi heap have pure quantum mechanical origin with no classical analog, and we see that they make sense and they do not violate any other general principle. Alright. So, this is about the wave function part. Now, what we will do, we will discuss a bit about the energies that we obtained for the excited states of helium atom. So, if you remember, we had these 2 energies as the first order energy correction to E1 and E2. E1 had the Coulomb integral minus exchange integral, E2 had Coulomb integral plus exchange integral. These energies I obtained when I considered the first 2 by 2 block of my 8 by 8 determinant. Now, if I do the same for the third and fourth, the second block, that means psi 3 psi 4 combination, in that case also I am not doing that explicitly, you can check for yourself, but overall matrix formulation would be same. So, therefore, the eigenvalues are going to have same overall appearance, except for the fact that this is also E3 is Coulomb integral minus exchange integral, E4 is Coulomb integral plus exchange integral, just like E1, E2, except for the fact that here the Coulomb integral is between 1s and 2p x orbital, and this is exchange integral between 1s electron and 2p x electron. And this is how E3 and E4 are different. So, they are positive and negative combination of the Coulomb and exchange operator between 1s and 2px. Similarly, I would see E5, E6 will be combination of 1s with 2py, E7 and E8 will be combination of 1s and 2pz, the Coulomb integral, exchange integral, the plus combination, the minus combination. So, in this case I would have the remaining energy terms, but one thing you would remember that when I am evaluating this Coulomb integral or exchange integral, 2px function, 2py function, 2pz function will have the same contribution, because my matrix element, the operator in my in that integral is 1 over r1 2. So, the angular parts would not have any differential contribution, rather only the radial part of the problem will influence the final integral value. So, therefore, for 2px, 2py, 2pz, the Coulomb integral and exchange integral are going to be same when I am considering their interaction with 1s electron. So, therefore, what I am going to write is that E3 will be equal to E5 and E7, because they are the lower part of the solution. E4 is going to be equal to E6 and E8. So, they will be higher energy solutions. So, in this way what I have is E1, E2 separate, E3, E4 separate. Now, I am saying that E3, E5, E7 will be having same first order energy correction, and E4, E6 and E8 will have again the same value of first order energy correction. Remember, E1 to E8, all these states had same energy without perturbation. So, now when I am adding some first order energy correction, I'll lift the degeneracy, and in case the first order energy correction is also going to be same, in those cases I will not be able to lift my degeneracy. Alright, we will discuss that in a slightly pictorial manner. Consider this as my ground state, where both the electrons are of helium atom in 1s orbital. I create excited state by exciting one of these two electrons from 1s orbital to either 2s, 2px, 2py, 2pz. These are the 4 states. Of course, I am in my wave function, I consider their exchange part as well. So, this has got 8-fold degeneracy. Now, what I am doing is that this excited state represents 8-fold degeneracy. They correspond to the unperturbed wave functions psi10 to psi80. Now, what I see is that each term has got some Coulomb integral. So, now I am introducing Coulomb integral. For this, first let us consider the E1, E2. So, I am considering this Coulomb integral. This Coulomb integral when gets added as a first order energy correction to this unperturbed state, and that takes this 1s1 2s1 state to some other value. I am adding this Coulomb integral between 1s electron and 2s electron. Similarly, I can now add the Coulomb integral between 1s and 2p electrons. So, that is J1s 2p, and that will take the 6 functions E3, E5, E7, E4, E6, E8, all of them to be degenerate. Mind you, why they are all degenerate, all 6-fold degeneracy? Because I have introduced only the Coulomb part. I have not talked about the exchange part. In the absence of the exchange part, they still have this so called exchange degeneracy. So, this state is 2-fold degenerate, this orange state is 6-fold degenerate. So, this degeneracy has exchange degeneracy because I still have not incorporated the exchange interaction. But just by introducing the Coulomb interaction, Coulomb integral, I can already split the 8-fold degeneracy into 2 different sets, one with 2-fold degeneracy, the other one is with 6-fold degeneracy. Now, one thing that you would notice here, that I am suggesting that the Coulomb interaction between 1s 2s electron is less compared to the same interaction between 1s and 2p. Why would that happen? We can easily rationalize this observation by looking at the radial distribution function. For example, this is the radial distribution function of 1s, 2s and 2p orbitals of hydrogen atom. You will see that the 2s orbital has got a higher probability to be found closer to the nucleus compared to 2p. So, in other words, 2s electron can penetrate closer to the nucleus. In another way to speak, that this 1s electron cannot shield the 2s electron from the nucleus, because 2s electron is able to penetrate closer to the nucleus. But this shielding of 1s electron is very effective when it comes to 2p electrons, because 2p electrons, the density is not that high closer to the nucleus. Now, how it matters? See, the Coulomb interaction comes when the electrons repel each other. Now, when it comes to 2s electron, it will face the repulsion from that part of the 1s charge cloud which is yet not penetrated, because the 2s electron is able to penetrate over the 1s charge density. So, this Coulomb interaction is coming when the two charge densities are interacting with each other. Since the 2s electron is already able to penetrate the 1s charge density, so therefore, the repulsion that 1s electron provides to 2s electron is only coming from those yet to be penetrated or the unpenetrated part of this 1s charge density, which is small. Now, that is why the 2s electron faces less repulsion from 1s electron. On the other hand, 2p electron cannot penetrate so close to the nucleus and therefore to the regime of 1s charge cloud. So, therefore, more amount of charge cloud of 1s electron are going to repel the 2p electron. So, therefore, the Coulomb interaction or the charge repulsion between 1s and 2p is going to be greater than what we see between 1s and 2s. So, that justifies why we would have this 1s 2s 1 state lower in energy compared to the 1s 2p configuration, because of the difference in Coulomb interaction. But still, we have just added the Coulomb terms. Now, what we will do is that we would add the exchange interaction. First, we will look at the 1s1 2s1 situation. When we add this exchange interaction, you would say that these two states will split by twice of this exchange integral. So, one gets lowered by k1s 2s, the other one gets shifted by k1s 2s. So, overall there will be a splitting of twice the exchange integral, and now here in this case we have lifted the so called exchange degeneracy. The exchange degeneracy came in when we had these constructed these wave functions by simply exchanging the two electrons among the 1s 2s pair. So, now that degeneracy is lifted because of this exchange interaction. Now, we have already repeated it several times. This exchange interaction will not be able to explain it away in terms of any classical analog. So, similarly, these orange states, which are now 6-fold degenerate, when I introduce the exchange interaction, so they would also get splitted, but they will also be splitted in each case to two levels, one with j minus k, the other one is j plus k. But remember, the 2px, 2py, 2pz, all these three quantities had same Coulomb integral and they also would have same exchange integral. So, therefore, the lifting of degeneracy that we see here is only within the two exchange pairs. So, that means one is 2px and 2px1s, these two exchange pairs get splitted. Similarly, 1s 2py, 2py1s, they get their degeneracy gets lifted. So, the degeneracy between the individual exchange pairs, those 4 blocks, within that block, that degeneracy has been lifted, but between one block and another block, that degeneracy is not lifted. So, each of these orange lines here, orange states here, is again got a 3-fold degenerate. They correspond to 2px, 2py, 2pz. Now, by incorporating the electron interaction, we cannot lift this degeneracies of the orange states. That's because they correspond to the magnetic quantum numbers, and those degeneracies can be lifted only when we have external field applied to them. So now at the end of this electron interaction, either Coulomb or exchange, we have lifted this 8-fold degeneracy to 4 different states, where the blue ones are non-degenerate and the orange ones are 3-fold degenerate. So we have all our 8 states, 3 plus 1, 3 plus 1. While the lowest and the highest states, their energies are standard. What is slightly tricky is to find the relative energy between the upper component of this 1s2s and the lower component of this 1s2p. They are very close to each other. The first order energy correction gives you this kind of picture, where the 1s2p state is lower than in energy. In fact, we can introduce their spectroscopic symbol. So the lowest of these 2 exchange pairs is the triplet state. We have seen that they correspond to the 510, which was antisymmetric with respect to orbital part of the electron exchange. So therefore, we coupled it with the triplet state, so that overall it remained antisymmetric. That gave me triplet S. The upper component 520, which was symmetric with respect to electron exchange when we consider only orbital, and then we coupled it with the singlet part of the spin function. So that gave me a singlet S state. So this is triplet S state, this is singlet S state. Now similarly, I have got triplet P and singlet P. This is the 530, this is 540 or 530, 550, 570, and here 5, 4, 6 and 8. So now we have got the triplets and singlet states of P and S symmetry based on where the second electron has been excited to S orbital or P orbital. Now the relative spacing of this triplet P and singlet S is slightly tricky. The first order energy perturbation correction actually gives this kind of arrangement, but when you incorporate higher order correction, you would see that the triplet P will have slightly higher energy than the singlet S, but this is matter of minor details. We would not worry about them, because once you incorporate the higher order energy corrections, your accuracy of the calculations would become better. So in this lecture, we learned about how we can use degenerate perturbation theory to study the excited states of helium atom. We saw that when we started the problem, we had 8-fold degeneracy in the first excited state of helium atom, but then by incorporating the electron-electron interaction either through Coulomb terms or exchange terms, we could differentiate the different excited states, which we could find triplet S, singlet S, triplet P, singlet P, and we also learned how these states arise or how the degeneracies are lifted by introducing the Coulomb interaction between them and the exchange interaction between them. We also discussed how the wave functions show interesting behavior in terms of the Fermi hole and Fermi heap. Of course, most of our wave function discussion was restricted to the first block of the problem, that is when the second electron was in 2s orbital, but you can take any other block when you put electron number 2 into px or 2py or 2pz and obtain the similar energy and similar wave function, and the similar analogous discussion can also be made for those states as well. So far what we have done is that we have looked at some problems where we could use perturbation theory either in a non-degenerate form or in degenerate form, and from next class onwards we will look at systems which have more number of electrons or which have larger number of nuclei, and how we can treat those systems using approximate methods in quantum chemistry. Thank you for your attention.